Hello students, in this lecture we will discuss how to solve the numerical problems pertaining to air standard cycle and the numericals that are related to basic performance parameters of IC engines. An engine running on Otto cycle receives air at 85 kilopascal, 280 Kelvin. If the maximum cycle pressure and temperature are 5 megapascal and 2000 Kelvin respectively, determine the temperature at the end of expansion stroke. So we have drawn here PV diagram, and you can also draw TS diagram as I have told you in the lecture class. So P1 is equal to 85 kilopascal and T1 is equal to 280 Kelvin. The maximum pressure of the cycle, that is at point 3, is 5 megapascal, that is 50 bar, or we can say 5000 kilopascal. Similarly, by the TS diagram you will come to know that the maximum temperature of the cycle is at point 3 and that is equal to 2000 Kelvin. Now as 1 to 2 is adiabatic process, we know the relation between pressure and volume, which we have expressed in equation number 1. Okay, so P2 upon P1 is equal to R raised to power gamma. Similarly, in the equation 2, we have represented the relation between the temperature and volume for an adiabatic process, and that is equal to T2 upon T1 is equal to R raised to power gamma minus 1. Now 3 to 4 is also an adiabatic process, and we are having the relation between pressure and volume for this adiabatic process 3 to 4 as expressed in the equation, that is P3 upon P4 is equal to V4 upon V3 raised to power gamma. Now V4 is equal to V1 and V3 is equal to V2. So the final expression become P3 upon P4 is equal to R raised to power gamma. Similarly, we are having the relation between temperature and volume as expressed in the equation on the slide. T3 upon T4 is equal to V4 upon V3 raised to power gamma minus 1, as V4 is equal to V1 and V3 is equal to V2. The final expression is T3 upon T4 is equal to R raised to power gamma minus 1. And on this slide we have shown the TS diagram also. So from equation 1 and 2 on the last slide we get this relation. P2 upon T2 is equal to P1 R raised to power gamma upon T1 R1. So finally we get this relation. And as you know, 2 to 3 is constant volume process. You can say P2 upon T2 is equal to P3 upon T3. So substituting these values, we get the final expression and the value of R as 8.235. Now we get the value of T4 as 860.5. A gasoline engine with a compression ratio of 10 receives air at 50 kilopascal and 280 Kelvin. Temperature at the expansion stroke is 750 Kelvin. If air can be assumed to be an ideal gas with the value of R equals 0.287 kilojoule per kg per Kelvin, determine the mean effective pressure for this cycle. So we have drawn the PV diagram and the TS diagram. Now here the value of compression ratio R is given as 10, P1 equals to 50 kilopascal, T1 equals to 280 Kelvin and T4 is equal to 750 Kelvin. Now for the state 1, we have written the state equation P1 V1 equals to RT1, where V1 is specific volume at state 1. So the value of specific volume at 1, that is V1, comes out to be 1.6072 meter cube per kg. Now since compression ratio is equal to 10, so that implies that V1 upon V2 is equal to R, that's equal to 10. So the value of V2 comes out to be 0.16072 meter cube per kg. Now we find out the efficiency of Otto cycle by the formula 1 minus 1 upon R raised to power gamma minus 1, and that comes out to be 0.60189. Now the value of T2, which is equal to T1 into R raised to power gamma minus 1, that comes out to be 703.33 Kelvin. Now T3 upon T4, that is equal to R raised to power gamma minus 1. So by this expression we calculate the value of T3, that comes out to be 1883.91 Kelvin. Now the heat supplied to the cycle is equal to CV into dt, that is CV into T3 minus T2, because 2 to 3 is heat addition process. So that comes out to be 847.7 kilojoules. Now the heat rejected, that is equal to CV into T4 minus T1, that comes out to be 337.46 kilojoule per kg. Now the mean effective pressure, which is equal to work done upon swept volume. Now work done we have calculated with the data given of heat supplied and heat rejected, because we know that work done is equal to heat supplied minus heat rejected. So the value of MEP comes out to be 352.58 kilopascal, and swept volume you must be knowing that is equal to V1 minus V2. An Otto cycle with a compression ratio of 10 receives air at 290 Kelvin, 85 kilopascal. If the peak cycle pressure is 6000 kilopascal, determine the highest temperature of the cycle. So we have drawn the PV diagram for the Otto cycle. The given parameters are the value of R, that is compression ratio, is 10, P1 equals to 85 kilopascal, T1 is equal to 290 Kelvin. The maximum pressure of the cycle, that is P3, is equal to 6000 kilopascal. Now we know the relation between the initial pressure, that is P1 and P2, and that is expressed by the equation number 1, P2 equals to P1 into R raised to power gamma. And similarly the temperature T1 and T2 are related by this expression, that is T2 equals to T1 into R raised to power gamma minus 1, given by the equation 2. So dividing equation first by equation second, we get this expression, P2 upon T2 is equal to P1 upon T1 into R. Now we know that 2 to 3 is a constant volume process, so we can write P2 upon T2 equals to P3 upon T3. So substituting the value of expression on the previous slides, that was given as P2 upon T2 equals to P1 upon T1 into R, we find out the value of T3 as 2047.06 Kelvin. In an air standard Otto cycle, the pressure and temperature of the air at the start of compression are 1 bar and 330 Kelvin respectively. The compression ratio is 8 and the energy added at constant volume is 1250 kJ per kg. Determine the following: maximum pressure and temperature of the cycle, air standard efficiency, specific volume at the start of compression, specific volume at the end of compression, mean effective pressure. Now the PV and TS diagram for the Otto cycle have been drawn. Now 1 to 2 is a reversible adiabatic compression process. 2 to 3 is constant volume heat addition process. 3 to 4 is reversible adiabatic expansion process, and 4 to 1 is constant volume heat rejection process. So the initial pressure, that is P1 is equal to 1 bar and T1 equals to 330 Kelvin. R, the compression ratio is 8. Therefore the heat supplied will be CV into T3 minus T2, and that is given as 1250 kilojoule per kg. Now as the process 1 to 2 is reversible adiabatic compression, the relation between the temperature and volume and that pressure and volume has been given. With the help of these, we can calculate the value of P2, that is coming out 18.38 bar, and the value of T2, that is coming out to be 758.14 Kelvin. Now as the process 2 to 3 is constant volume heat addition, so with the help of the expression given, that is CV into T3 minus T2, which is equal to 1250, we can calculate the value of T3, and that is coming out to be 2499.08 Kelvin. Now as the process 2 to 3 is constant volume process, so we can write P2 upon T2 equals to P3 upon T3. With this we get the value of P3, that is coming out 60.58 bar. Now the Air standard efficiency can be calculated with the help of this expression, that is 1 minus 1 upon R raised to power gamma minus 1. And with the help of this expression, the value of air standard efficiency comes out to be 56.47%. With the help of state equation at state 1, that is P1 V1 equals to RT1, we can calculate the value of V1, and that is coming out to be 0.9471 meter cube per kg. As the compression ratio is 8, so the value of V2 is coming out to be 0.11838 meter cube per kg. Now work done is equal to air standard efficiency into heat supplied, so this comes out to be 705.9 kilojoule per kg. Mean effective pressure is nothing but work done upon swept volume, and swept volume is V1 minus V2, and that is coming out to be 0.82872 meter cube per kg. So MEP comes out to be 851.79 kilopascal. In an air standard diesel cycle, the pressure and temperature of the air at the start of compression are 1 bar and 330 Kelvin respectively. The compression ratio is 16 and the energy added at constant pressure is 1250 kilojoule per kg. Determine the following: maximum pressure and temperature of the cycle, air standard efficiency, specific volume at the start of compression, specific volume at the end of compression, and mean effective pressure. Now the PV and TS diagram for the cycle has been drawn. 1 to 2 processes: reversible adiabatic compression, 2 to 3 is heat addition at constant pressure, 3 to 4 is reversible adiabatic expansion, and 4 to 1 is heat rejection at constant volume. Now P1 equals to 1 bar, that is 100 kilopascal, P1 equals to 330 Kelvin, and the compression ratio, which is V1 upon V2, that is equal to 16, and heat added during constant pressure heat addition is equal to Cp into T3 minus T2, and that is given as 1250 kilojoule per kg. Now as 1 to 2 process is a reversible adiabatic process, the relation between pressure and volume and the relation between temperature and volume is being given in the terms of compression ratio and gamma, that is ratio of specific heats. So with the help of these expressions, we can find out the value of P2, that is coming out to be 48.5 bar, and the value of T2, that is coming out to be 1000.37 Kelvin. Now as the 2 to 3 process is constant pressure heat addition process, so Cp into T3 minus T2 is equal to 1250. With the help of this expression, we can get the value of T3, that is coming out to be 2244.15 Kelvin. Now as 2 to 3 process is constant pressure process, so we can write V2 upon T2 equals to V3 upon T3. Now cutoff ratio, which is the ratio of V3 and V2 and also T3 and T2, as it is constant pressure process, so rho, which is equal to T3 upon T2, is coming out to be 2.243. Now the value of air standard efficiency can be computed with the help of this formula, and that is coming out to be 0.6022. For the state 1, we write the state equation P1 V1 equals to RT1, and with the help of this expression, we find out the value of V1, that is coming out to be 0.9471. Remember again that pressure has to be kept in kilopascal, as volume is in meter cube per kg, that is, it is a specific volume. R is in the units of kilojoule per kg per Kelvin, and temperature is having the value in Kelvin. As we know that the compression ratio is 16 and the compression ratio R is equal to V1 upon V2, so the value of V2 comes out to be 0.05919 meter cube per kg. And with this, the swept volume V1 minus V2 comes out to be 0.8879 meter cube per kg. Mean effective pressure, which is equal to work done upon swept volume, is found out to be 847.79 kilopascal, where you have substituted the work done equals to air standard efficiency into heat supplied. An engine working on the constant volume cycle has a compression ratio of 8:1. It uses petrol having a calorific value of 44,000 kilojoule per kg. If the brake thermal efficiency of the engine is 60% of the air standard efficiency, determine the brake specific fuel consumption in kg per kilowatt hour. Constant volume cycle means Otto cycle. Now the air standard efficiency of Otto cycle is equal to 1 minus 1 upon r raised to power gamma minus 1, which comes out to be 0.5647. Now brake thermal efficiency is given as 60% of the air standard efficiency, and brake thermal efficiency is equal to brake power divided by mf dot into cv, where mf is the fuel consumption rate in kg per hour and cv is the calorific value of the fuel. So basically numerator is the output, means the power that is generated by the engine as useful power that is available on the brake drum, and the numerator of this expression brake thermal efficiency is mf dot into cv, which is nothing but which is the rate of energy generated by burning of the fuel, by the combustion of the fuel. Now it is clear that both the terms numerator and denominator given in the second last expression of the slide has to be expressed in either kilojoule per minute or kilojoule per hour or kilojoule per second, that is kilowatt. Okay, then and then only the efficiency term will be unitless, will be dimensionless. Now we divide the numerator and denominator of this expression by brake power and we get the expression as is seen on the last equation of the slide. Now BSFC, brake specific fuel consumption, which is expressed in kg per kilowatt hour, is nothing but rate of fuel consumption in kg per hour per unit of power, useful power generated by the engine, and that is in kilowatt. So BSFC has the unit of kg per kilowatt hour. Now you have put all the terms that is known to us in the equation that was given on the last of the previous slide. So basically BSFC comes out to be 6.7074 into 10 raised to power minus 5 kg per kilojoule. Why so? Because you see on the left hand side, which is efficiency and which is expressed as 0.6 into 0.5647, that is bearing no unit because it is basically the value for brake thermal efficiency. On the right side of this equation, we are having 1 upon BSFC into 44,000 kilojoule per kg. Now you know that numerator is having no unit and denominator has also to be unitless. So what unit calorific value is having, BSFC is going to have reciprocal of that. Means since calorific value is having unit of kilojoule per kg, BSFC ought to have the unit kg per kilojoule in order to have denominator unitless. Okay, so that is why we have got the unit of BSFC as kg per kilojoule. I think that must be clear now. Now the BSFC has to be expressed actually in terms of kg per kilowatt hour. So what we have done, we have multiplied it with 3600 second per hour, because you know that kilojoule can be written as kilowatt second. Okay, so the answer comes out to be in kg per kilowatt hour. So that is how you have converted the unit of kg per kilojoule into kg per kilowatt hour, because kilojoule can be written as the product of kilowatt second. An engine working on Otto cycle has clearance of 17% of stroke volume, an initial pressure of 0.95 bar and temperature of 30 degrees Celsius. If the pressure at the end of constant volume heating is 28 bar, determine an air standard efficiency, maximum temperature of the cycle, mean effective pressure. Now we have drawn the PV diagram, and for each processes the governing equation has been written on the PV diagram itself. Now as per the question given, Vc is equal to 0.17 of Vs, as it is given that clearance is 17% of the stroke volume. Now P1 is equal to 0.95 bar, T1 which is equal to 30 degrees Celsius is equal to 303 Kelvin, and P3 is equal to 28 bar, because it is written that the pressure at the end of constant volume heating is 28 bar, so it is nothing but P3. Now the compression ratio, which is equal to Vc plus Vs upon Vc, so it can be written as 1 plus Vs upon Vc, and Vc we have substituted with 0.17 of Vs, so this gives us the value of compression ratio to be 6.882. So once we have found out the value of compression ratio, we can find out the value of air standard efficiency for Otto cycle given by the formula 1 minus 1 upon r raised to power gamma minus 1, and that comes out to be 0.5377. Now we have drawn TS diagram here for the Otto cycle. Now process 1 to 2 is basically reversible adiabatic compression process. So the relation between pressure and compression ratio is given by the formula P2 is equal to P1 into r raised to power gamma, and the value of P2 comes out to be 14.142 bar. Similarly, the relation between the temperature and compression ratio comes out to be T2 equals to T1 into r raised to power gamma minus 1, and the value of T2 comes out to be 655.43 Kelvin. Now for constant volume heat addition process, that is indicated by the process 2 to 3, P2 upon T2 equals to P3 upon T3. So with this we get the value of T3 equals to 1297.7 Kelvin. Now heat supplied during the constant volume heat addition process is equal to Cv into dt, that is Cv into T3 minus T2, and that comes out to be 461.148 kilojoule per kg. Now with the help of state equation, that is P1 V1 is equal to RT1, the value of V1 comes out to be 0.91538 meter cube per kg. Here you have put pressure in kilopascal. Now since V1 upon V2 is equal to R, so we have found out the value of V2 equals to 0.13301 meter cube per kg. Now as the value of mean effective pressure can be calculated with the help of formula work done upon swept volume, and work done is equal to air standard efficiency into heat supplied, the mean effective pressure comes out to be 316.93 kilopascal. A 4-cylinder 4-stroke SI engine gave the following particular when tested: bore is equal to 6.5 cm, stroke equals to 9.5 cm, speed equals to 3000 rpm, clearance volume 65 cm cube, brake thermal efficiency 60% of air standard efficiency, torque developed is equal to 70 Newton meter, calorific value of fuel 46,000 kilojoule per kg. Determine the compression ratio, air standard efficiency, brake mean effective pressure, brake specific fuel consumption. Now we have drawn PV diagram, and on the PV diagram, on all the processes involved in the cycle, the governing equations have been written. Now swept volume is equal to pi by 4 d square L, where d is the bore size and L is the stroke length, and both has to be kept in meter so that we can have the value of swept volume in meter cube. Now the swept volume comes out to be 3.1524 into 10 to the power minus 4 meter cube, and the clearance volume, which is given as, can be written as 65 into 10 to the power minus 6 meter cube. Now R, the compression ratio, is equal to Vs plus Vc upon Vc. So its value comes out to be 5.85 by putting the values in the formula. Now, as we are having the value of compression ratio now, so we can find out the value of air standard efficiency with the help of formula 1 minus 1 upon r raised to power gamma minus 1, and this value comes out to be 0.50666. Now the brake thermal efficiency has been given as 60% of the air standard efficiency, so its value can be computed with the help of this value. Now brake thermal efficiency is also expressed formula wise as the ratio of brake power and the energy generated by the burning of the fuel, that is mf dot into cv, where mf dot is basically the fuel consumption rate and cv is the calorific value. Mf dot is basically put in kg per second and cv is put in kilojoule per kg, so that the denominator is basically having the unit of kilojoule per second, as the numerator is expressed in kilowatt itself, so both are having the same unit. Now the brake power, which is equal to 2 pi nt upon 60. Now n is given as 3000 rpm and the torque is given as 70 Newton meter. So with the help of these values given, we find out the value of brake power is equal to 21.99 kilojoule per second. Now the brake power, which can also be expressed by this expression PBM, that is brake mean effective pressure, into L A N into number of cylinders upon small n, where small n is number of revolutions required to complete one working cycle. Now this value of n is equal to 1 for 2 stroke and it is having the value of 2 for 4 stroke. L is basically nothing but stroke length. A is nothing but cross-sectional area of the cylinder. Capital N is the speed of the engine, which has to be expressed here in revolutions per second. Now we are substituting the given values in the formula. So the value of brake mean effective pressure comes out to be 697.6 kilopascal. Now brake thermal efficiency, which is equal to brake power upon mf dot into calorific value, which is also equal to 0.6 into air standard efficiency. So the value of brake thermal efficiency comes out to be 0.304. Now we divide the formula expression for the brake thermal efficiency, that is its numerator and denominator, by brake power. So we get the formula brake thermal efficiency is equal to 0.304, which is equal to 1 upon BSFC into calorific value. So the value of BSFC comes out to be 1 upon 0.304 into 46,000. Now the value of BSFC is 7.151 into 10 to the power minus 5 kg per kilojoule, and kilojoule can be written as kilowatt second, and we know that 1 hour is having 3600 seconds, so we multiply this conversion factor and we get the value of 0.2574 kg per kilowatt hour. In an ideal diesel cycle, the pressure and temperature at the beginning of compression are 98.5 kilonewton per meter square and 60 degrees Celsius respectively. The maximum pressure attained during the cycle is 4.5 meganewton per meter square and the heat received during the cycle is 580 kilojoule per kg of working fluid. Determine A, the compression ratio, B, the temperature at the end of compression, and C, the temperature at the end of compression. Now PV and TS diagram for the diesel cycle has been drawn on the slide. Heat addition is taking place at constant pressure in the diesel cycle and heat rejection is taking place at constant volume. Now P1 is equal to 98.5 kilonewton per meter square, T1 equals to 333 Kelvin, P2, which is equal to P3, has been given as 45 bar. Now the heat addition, which is equal to Cp into T3 minus T2, that is equal to 580 kilojoule per kg. Now 1 to 2 is adiabatic compression process, for which the relation between temperature and volume has been given as T2 upon T1 is equal to V1 upon V2 raised to power gamma minus 1. and since V1 upon V2 is R, so T2 upon T1 is equal to R raised to power gamma minus 1. Similarly, the relation between pressure and the compression ratio is also expressed as P2 upon P1, which is equal to R raised to power gamma. So now we have divided these two expressions in order to get the value of compression ratio, and that comes out to be 15.33. Now the value of T2 comes out to be 992.3 Kelvin. Substituting the value of the heat supplied and the value of Cp and the value of T2 in the expression for the heat addition, the value of T3 comes out to be 1569.4 Kelvin. A diesel cycle has a compression ratio of 20 with an inlet state of 95 kilopascal, 290 Kelvin, and a maximum cycle temperature of 1800 Kelvin. If air can be assumed to be an ideal gas with R equals 0.287 kilojoule per kg per Kelvin and CV equals to 0.717 kilojoule per kg per Kelvin, determine the net specific work output from the cycle. Now we have given the PV diagram for the diesel cycle. The compression ratio is 20, P1 equals to 95 kilopascal, T1 equals to 290 Kelvin. The T maximum, that is the temperature at point 3, is 1800 Kelvin. Value of R and CV has been given. Now P2 equals to P1 into R raised to power gamma. So this gives us the value of P2 as 6297.4 kilopascal. And T2, which is equal to T1 into R raised to power gamma minus 1, comes out to be 961.2 Kelvin. Rho, which is equal to T3 upon T2, comes out to be 1.87. Now T4 upon T3, which is equal to V3 upon V4 raised to power gamma minus 1, and which is eventually rho upon R raised to power gamma minus 1. This basically expression will give us the value of T4, and that comes out to be 697.6 Kelvin. Now the heat added, which is equal to Cp into T3 minus T2, comes out to be 842.15 kilojoule. And the heat rejected, that is equal to Cv into T4 minus T1, comes out to be 292.23 kilojoule per kg. Now the net work, which is equal to QH minus QL, comes out to be 549.92 kilojoule per kg. A diesel engine receives air before compression at 280 Kelvin and 85 kilopascal. The highest temperature and the pressure of the cycle are 2200 Kelvin and 6 megapascal respectively. If air can be assumed to be an ideal gas with R equals to 0.287 kilojoule per kg per Kelvin and CV equals to 0.717 kilojoule per kg per Kelvin, determine the mean effective pressure of the cycle. Now we have drawn the PV diagram for the diesel cycle. P1 equals to 85 kilopascal, T1 equals to 280 Kelvin. Now the value of T3 is equal to 2200 Kelvin. Now the value of Pmax, which is equal to P2 and which is also equal to P3, is equal to 6000 kilopascal. Now P2 is equal to P1 into R raised to power gamma. So the value of R that is calculated with the help of this expression comes out to be 20.918. T2 is equal to T1 into R raised to power gamma minus 1. So with this expression, the value of T2 comes out to be 944.9 Kelvin. Rho, which is equal to T3 upon T2, is equal to 2200 upon 944.9, that comes out to be 2.3283. We have drawn TS diagram for this cycle, that is diesel cycle, on the slide. Now the heat added is equal to Cp into T3 minus T2, and that comes out to be 1260.16 kilojoule. Heat rejected, which is equal to Cv into T4 minus T1, comes out to be 454.71 meter cube per kg. 454.71 meter cube per kg. Now for state 1, with the help of state equation, we can determine the value of V1 and that comes out to be 0.9454 meter cube per kg. Now V1 upon V2 is equal to R compression ratio. With this expression we can determine the value of V2, and that comes out to be 0.045196 meter cube per kg. Mean effective pressure, which is equal to work done upon swept volume, comes out to be 894.744 kilopascal. A cycle working on ideal dual combustion cycle receives 2/3 of the total heat supply at constant volume and rest at constant pressure. It has a compression ratio of 9. State at the beginning of compression is 90 kilopascal, 20 degrees Celsius, and it receives 2100 kilojoule of heat per kg of the working fluid. If air can be assumed to be an ideal gas with R 0.287 kilojoule per kg per Kelvin and CV equals to 0.717 kilojoule per kg per Kelvin, determine the thermal efficiency of the cycle. Now we have drawn the PV diagram for the dual cycle. 1 to 2 is reversible adiabatic compression process, 2 to 3 is heat addition at constant volume, and 3 to 4 is heat addition at constant pressure. So here in this dual cycle, as I told you in the lecture class, combustion is partly taking at constant volume and partly at constant pressure. So 2 to 3 is heat addition or combustion at constant volume, and 3 to 4 is heat addition or combustion at constant pressure. Now 4 to 5 is reversible adiabatic expansion, and 5 to 1 is heat rejection at constant volume. So the value of P1 is 90 kilopascal, the value of compression ratio is 9, and T1 is equal to 293 Kelvin. Now heat addition at constant volume is 2/3 of 2100 kilojoule per kg, that comes out to be 1400 kilojoule per kg, and the remaining, that is heat addition at constant pressure, which is equal to 1/3 of 2100 kilojoule per kg, that comes out to be 700 kilojoule per kg. We have drawn the TS diagram. 1 to 2 is reversible adiabatic compression, that is isentropic, so it is shown by the vertical line on TS diagram. Now 2 to 3 is heat addition at constant volume, and 3 to 4 is heat addition at constant pressure. Now you can see the difference between 2 to 3 curve and 3 to 4 curve. 2 to 3 is constant volume curve, so it is having higher slope than a isobaric curve, that is 3, 4. Now 4 to 5 is reversible adiabatic expansion. Again it is isentropic process, so it has to be shown by vertical line on the TS diagram. And 5 to 1 is heat rejection at constant volume. Now T2 equals to T1 into R raised to power gamma minus 1, so that comes out to be 705.6 Kelvin. CV into T3 minus T2, that is heat addition at constant volume, is given at 1400 kilojoule per kg. So this gives us the value of T3, which is comes out to be 2658.18 Kelvin. Now heat addition at constant pressure has been given 700 kilojoule per kg. So this gives me the value of T4, which comes out to be 3354.7 Kelvin. Now T4 upon T5, which is eventually R upon rho raised to power gamma minus 1. So the value of rho, which is equal to V4 upon V3 and also T4 upon T3, comes out to be 1.262. So now with the value of rho we can have the value of T5, and that comes out to be 1528.9 Kelvin by the expression given for T4 upon T5, which was equal to R upon rho raised to power gamma minus 1. Now we are having all the values of temperatures, and the formula of efficiency here shown on the slide is given in the terms of temperatures and Cp and Cv. So we are having all the values, means all the temperatures and the value of Cp and Cv, so we can calculate the value of efficiency, and that comes out to be 0.5778. This is all for the numericals for the air standard efficiency of Otto, diesel and dual cycle, and the performance parameters.